All right, I mentioned the other day that we were going to go through a couple demos. So the first thing that I mentioned was this distance doodler that you can get at any toy store. It's glow-in-the-dark paper with LED or ultraviolet laser. Comes with it. That ultraviolet laser looks like this. It's got a little button for the laser pointer, and it's got a little button for fiber optics, so you can talk about total internal reflection as well with that if you'd like. This was a great buy for me, but you can find these on Sergeant Welch. I think they're like $5 or $7 per sheet for photosensitive paper, which is kind of a pain. So finding it in a kit at a toy store is actually ideal because it usually comes with other stuff like this. The other thing that I do is diffraction in class, and we talk about the waves as they enter an opening or exit an opening. They tend to split out and spread out. So what we're going to do is take a look at rainbow glasses, and the idea that when you look through rainbow glasses, there's small little lines in there, and the wave travels through and then exits that opening and splits as it enters your eye, so you're able to see all the colors when you look at your standard lights in the room. So that's the rainbow glasses. Having a set of those around is really, really nice. Along those same lines, you can actually shift into the old diffraction gratings, which are basically the exact same material. These are 530 lines per millimeter. You can use these to look through and you still see the rainbows. I have my kids actually measure with trig. They shine a laser through this and they figure out what the distance between the lines is on this. But I wouldn't go that deep with 1A, but it still would be a great demonstration of, hey, it looks clear, but there's actually these little fence posts, so to speak, for the light to get through. Once you have done diffraction gratings, it's interesting, you can actually talk about the fact that as you fire a laser beam into something like a CD, the laser beam enters the CD and then the track is a certain width. So what we have, here's a green laser, and that track is a certain width. So as I fire the laser in, it goes in, it reflects, it comes back out. As it comes back out, it diffracts as it exits the track. So what we can do is use that knowledge to shine a laser into the track, and then as it comes back out, we get a diffraction pattern from that CD track. So we can use that diffraction pattern and a little bit of trig and an equation to figure out exactly how wide the width of a track on a CD actually is. And based on that, we can talk about data storage capacity. Once you've done the CD though, you can go one step further, okay? I recommend a season of something so you have multiple DVDs, or you can just bring them in from home. Kids always ask, you know, Xbox games, are they the same? Have them bring them in. Have them test them with the laser. And once you figure out that DVDs have a smaller track width, why do we use a different wavelength of light to read DVDs than we do CDs, right? And of course, when do we go to Blu-ray? What happens there? Well, Blu-ray gets its name because we use a different colored light for that slit or that track width. I wonder how blue is different than red in terms of the knife that's able to get into that track and read it. Blue has a smaller wavelength, which means it's able to get into the smaller track. So red lasers are great, but green seems to be good for most of the CDs, DVDs. Obviously red is too big for any Blu-rays or anything like that, or HD DVDs. But if you want to bring those in, you can. The other extension activity, I always ask them, you know, we can go real old school with Top Gun here. It's an old movie, but it's also old media. As it turns out, this is called a laser disc. Most people my age probably have no idea what this is, but it's a laser disc, and it's essentially the original DVD. It's a movie with audio and video, and it has the same track width as the CD. So if you shine a laser at this one, you'll be able to see, essentially it's the exact same diffraction pattern that we had before with the CD. So we are able to measure, hey, the CD track width and the laser disc track width are the same, so what was the big breakthrough? Well, there really wasn't one when we went from laser discs to CDs. It's just what plays them is much smaller, so you can fit it in your car and things like that. Unfortunately, the CD generally isn't able to have things like video and larger data storage capacity on it, so you're stuck with these when you want video until we got to DVDs and got that laser a lot smaller, a higher frequency, lower wavelength, and we're able to read the DVD. So at this time, I'm gonna go ahead and stop the video, and we're gonna, actually no, excuse me, there's one more thing. We do measure human hair using this same method. And there's essentially, if you cut a hole in a notebook or a notebook card and note card, and you put a laser through the hair that you've mounted across that hole, you can actually measure by shining a laser. You can actually see a diffraction pattern when it hits that hair, and based on that, you have to be about 10 meters away from your screen, but you can actually take measurements on the screen and work backwards with trig to figure out the width of the human hair. So that's a all one day lab, but they're able to measure their own hair, the width of the human hair, and it's usually somewhere between 50 and 150 microns is what you get for that. So depending on ethnicity, we see some trends there, so you can actually bring that about if you'd like in your class. I'm not sure how much of this you'd actually do in a 1A course, but it's great for a demonstration, even if you just do it as we just did today. So we're going to go ahead and stop the video. The next video that you see will be the LED demonstration where we talk about the photoelectric effect. So I'll see you in a sec.